Good morning, class. Let's now move on to Bayesian belief networks, presented as your 7th lecture under module 4. Is the presentation visible?
Yes, ma'am.
Okay. In the last class, we have gone through the concept of naive-Bayes classifier. How naive-Bayes classifier can be used to implement the naive-Bayes approach in order to draw some inferences to using probabilistic approach. In today's class, we are going to see Bayesian belief networks and what is the difference between Bayesian network and Bayesian learning and Bayesian belief networks. Bayesian theorem, Bayes theorem, how is it different from Bayesian belief networks? We are going to understand. Now, the naive-Bayes classifier assumes that all the variables are conditionally independent given the value of the target variable. So you remember in the previous class, we have calculated the probability of playing tennis on a particular day, whether it is yes or no. We calculated the probability, and based on the highest probability, we are able to assign that label, whether it is yes or no. Tennis is played on that day or not. Right, given the weather conditions. And while calculating this, we have considered that each of the attributes, sky, humidity, outlook, all these variables, we thought them, we considered them, we assumed them as conditionally independent. Right, that is why we calculated probability of humidity given S, probability of wind being strong given S, and in the same way probability of wind being strong given no. For every attribute, we try to find its relation with the outcome label or the target label, right? We did like that because of the assumption that the variables are conditionally independent. They don't have any relationship with each other. Means, say, sky being cloudy doesn't determine the outlook being overcast or the outlook being sunny. Means one attribute value doesn't determine the other attribute's value. Right? In that case, we call them as conditionally independent variables. So the naive-Bayes classifier, what assumption it makes is all the variables, all the attributes are conditionally independent given the value of the target variable. Did you understand what is conditionally independent now? Now, if I say lightning and after that thunder, light travels faster, right? So lightning occurs first, then thunder. So that we can determine that thunder is dependent on lightning. Means those two are conditionally dependent variables. But in this case, in naive-Bayes classifier, we thought that we assumed that all the variables are conditionally independent. Right? If you take a rainy day, on a rainy day, we make a cup of coffee, hot cup of coffee. Means when we make hot cup of coffee, don't go into too much realistic approach. I'm just giving you an example. If you make a cup of coffee, hot coffee, then we assume that it might have rained on that day. Means we are making this hot cup of coffee conditionally dependent on raining. Okay, that is how we mention conditional dependence. But naive-Bayes classifier assumes that all the variables are conditionally independent given the target variable. That is why we have applied the formula in the previous class with respect to each and every attribute given the target variable, and we calculated the probability of playing tennis on a particular day, whether it is yes or no, given the weather conditions, climatic conditions. Right? But what does Bayesian belief network do? It allows stating conditional independence assumptions that apply to subsets of variables. Again, you have to note this, underline this particular sentence. subsets of variables. In Bayesian belief networks, we can state the conditional independence as allow stating conditional independence assumptions that apply to only subsets of variables. Means some variables in a training set are conditionally independent, but some are conditionally dependent. Okay, means one variable has some dependency on the other variable. Means if one variable occurs, it increases the probability of other variable occurring. The probability of a rainy day will increase the probability of making a hot cup of coffee. Did you understand? Now, having a bus tour group to a particular place, it increases the chances of setting up a campfire. And if it is cool, it increases the probability of setting up a campfire. Means probability of one variable, if at all, it increases or decreases the probability of the other variable. In that case, we say they are conditionally dependent. In Bayesian belief networks, we need not outrule entirely this conditional independence assumption. For some subsets of variables, we can assume this conditional independence, and some subsets of variables, we can assume they are conditionally dependent. Right? So whenever you have some subject matter expert or whenever you have a domain expert who is also involved in developing a machine learning model, now they can give you ideas about which variables are conditionally dependent, which variables are conditionally independent. Based on that, your work will be easier. You can set up this Bayesian belief networks. What is the use? Why do you need to see whether the variables are conditionally dependent or independent? Say, in some cases, there are some parameters which may not be measurable. Say, when you take rocket combustion cabin, right? In that fuels will be burning at a high temperature. They'll be burnt at a high temperature to exert pressure to launch the rocket, right? In that case, how much, what exactly is the fuel consumption inside the fuel cabin? Can you go and measure directly? No. You can put a sensor, but still, if at all, a particular burning rate can be measured from the fuel consumption into the temperature or something as an equation. Pressure multiplied by temperature or pressure multiplied by humidity. If at all the consumption rate can be measured as an equation of other measurable variables, then you need not actually measure this consumption. Correct? Say if I want to calculate the force, then mass into what is the formula for force? Mass into velocity. Okay, if I'm wrong, correct me. I don't remember much. Force is mass into velocity. If at all we write like this, then you need not calculate this force directly if it is hard to measure it. You understood? If at all force is hard to be measured, in some circumstances, don't measure force, but derive it as a multiplied value of mass and velocity. It is easy, right? You are able to measure mass, you are able to measure velocity of something. Now, you need not measure force because it is hard to measure in some circumstances. In that case, you can derive force as product of mass into velocity. Why? Why? Because you're making an assumption that force is dependent on mass and velocity. Force is conditionally dependent on mass and velocity. If it is conditionally dependent, it can be derived by establishing an equation between the measurable quantities. So what you're doing here is hard to measure quantities you're deriving from easily measurable quantities because of assuming that they have conditional dependence. That is why in some cases where you can't measure some attributes directly, you can set them up as a equation. You can derive them as an equation of other measurable attributes by assuming they are conditionally dependent. That is where this Bayesian belief networks will be useful. Okay, but now see the second point. I think it will make more sense for you now than before. But Bayesian belief networks allow stating conditional independence assumptions that apply to subsets of variables and assuming that other subsets of variables are conditionally dependent because they have some meaningful relation in the context, in the domain, in the field which we are considering, right? It is an intermediate approach that is less constraining. Now it is less constraining, right? We didn't say that it is all the variables are conditionally independent or all the variables are conditionally dependent. We are just saying that subsets of the variables, some part of the variables are conditionally dependent and some part of the variables are conditionally independent, right? So it is an intermediate approach that is less constraining, having lesser restrictions than the global assumption of conditional independence made by the Bayes classifier. But in this case, it is more tractable, it is more manageable, it is under our control. Okay, it is more tractable than avoiding conditional independence assumptions altogether. Do not eliminate the assumption of conditional independence altogether. Assume that some part of the attributes are conditionally independent and some part of the attributes are having some relationship. They are conditionally dependent. One probability of one variable may increase or decrease the occurrence of another variable, probability of another variable. That is called conditional dependence. Do you have any doubt with this term, students? Conditional dependence and conditional independence?
No, ma'am.
Good. So let us go to actual explanation of Bayesian belief networks by using some mathematical representation so that you can easily calculate the conditional joint probability distributions. Okay. I'm trying to make each and every mathematical concept clear from the basics for you. So if at all it is out of your understanding capability, just go through the video 2 to 3 times. That's all. You'll easily understand. Okay. Now, in general, a Bayesian belief network describes the probability distribution over a set of variables. So what do you understand about Bayesian belief networks? They describe, they explain the probability distribution over a set of variables. If you have multiple variables, what is the probability distribution across them? So that some of them happen together, some of them are independent. Okay, some of them are dependent and some of them are independent. Now consider an arbitrary set of random variables y1 and so on up to yn, where each variable yi can take on the set of possible values v of yi. What we are assuming here, we are taking some random variables. Random variables means they are not taken according to some planned action. You just pick them randomly. Say humidity equal to one particular day's climatic conditions. Those are set of random variables, right? Another day, can you say that these will be the variable values? No. The next day, the climatic conditions may differ, right? So consider such kind of arbitrary set of random variables, y1, y2, and so on up to yn, each having set of possible values v of yi. Say for sunny, for sky attribute, you can have sunny, cloudy, and normal. For humidity, low, medium, and high. Like that, set of attributes are indicated, set of attribute values are indicated by v of yi. Okay, we define the joint space of the set of variables y to be the product, to be the cross product of v of y1 multiplied by v of y2 and so on up to v of yn. What do you mean by this joint space? Joint space of the set of variables means how many values are allowed for sunny? 3 values. How many values are allowed for humidity? 2 values. How many values are allowed for outlook? 2 values. So it is 3 into 2 into 2. So it is total 12 combinations you get in the joint space of the set of variables y. Is it very clear now? Now the probability distribution over this joint space is called the joint probability distribution. Now, if you assign a probability distribution to this joint space of 12 combinations, then you call that as joint probability distribution. The probability is distributed jointly across all these combinations. What is the probability of occurrence of first combination? What is the probability of occurrence of second combination? When you assign such probability to it, then we call it as joint probability distribution. You distributed the probability jointly to all the occurrences in the joint space. Okay, so the joint probability distribution specifies the probability for each of the possible variable bindings for the tuple y1, y2 and so on up to yn. Right? So this joint probability will specify the probability for each of the possible variables. What is the probability of this combination of attributes? What is the probability of this combination of climatic conditions on a particular day? What is the probability of this set of climatic conditions on a particular day? The probability is assigned to all the possible combinations. Okay, that is called as joint probability distribution. Why we are calling it as a tuple? It has various values, right? 12 different values it can have. If it has 3 attributes, first attribute having 3 values, second attribute having 2 values, and third attribute having 2 values. Total, how many combinations you get in the joint space? 3 into 2 into 2. So you get total 12 combinations. Each of that is indicated as a tuple of combinations, right? And for each of them, probability is assigned, which you call as joint probability distribution, right? Now let us understand the idea of conditional independence. Once again, more clearly. I have given you an example, but did you understand it mathematically? So let us see how it is represented mathematically. We say that x is conditionally independent of y given z. This is a quite tricky sentence. You have to remember, practice it. When I read about these two terms, go back each time and see how it is written as a text. Okay? So far, we have understood that P of x given y. Right? But here that notation is read in a little different way. Listen carefully. We say that x is conditionally independent of y given z. I'm reading it again. We say that x is conditionally independent of y. X is not dependent on y given z. If at all z is given, which may have some conditional independence on x, but y doesn't have any, conditional dependence on x, z has conditional dependence on x, it may have conditional dependence on x, but y will not have any dependence on x. X also doesn't have any dependence on y. We say that x is conditionally independent of y. Given z, if the probability distribution governing x is independent of the value y given a value z, that is, let us see the mathematical notation. Once again, we'll go back. That is, if you take a variable value xi, yj, and zk, you can represent this conditional independence as probability of x having the value xi is conditionally independent of y having the value yj given z equal to zk. Okay, initially we used to read it as x given y. Now we can't read it as x given y comma z. You should read it as X is conditionally independent of Y given Z. Got it? In that case, we understood that X have some conditional independence from Y. So you can eliminate this. Finally, write it as P of X given Z. Did you understand? According to this statement, X is conditionally independent of Y given Z. When X is conditionally independent of Y, you can eliminate that from the equation. You can eliminate from the representation, and you can write it as P of X taking the value Xi given Z taking the value Zk, which indicates that X is actually dependent on Z but not on Y. Got it? Where Xi belongs to possible values of X attribute, Yj belongs to possible values of Y attribute, Zk belongs to possible values of Z attribute. Right? Now we commonly write the above expression in the abbreviated form as, for simplicity's sake, we can write it like this. Instead of X equal to Xi, X means it represents all possible values of X. So you can simply write it as, I'm reading it again, probability of X being conditionally independent of Y given Z, you can write it as probability of X given Z directly by eliminating Y, because X is conditionally independent of Y. X doesn't depend on Y's value. That is why you have eliminated and you have written it as P of X given Z. Now the definition of conditional independence can be extended to sets of variables as well. Not only single variable, you can apply it to sets of variables also. And that notation is also very easy to understand. We say that the set of variables x1, x2 and so on up to xl is conditionally independent of the set of variables y1, y2 and so on up to ym, given the set of variables z1, z2 and so on up to zn. How do you represent that? It is very easy, right? P of X conditionally independent of Y given Z. That is how you represent, right? Now instead of X, we are assuming the set of variables. That is why you write x1, x2 and so on up to xl. Probability of x1, x2 and so on up to xl is independent, conditionally independent of the set of variables y1, y2 and so on up to ym, given the set of variables z1, z2 and so on up to zn. Now because you know that X is conditionally independent of Y, you can eliminate this term and simply write it as probability of x1, x2 and so on up to xl given z1, z2 and so on up to zn, which indicates that X may be dependent on Z but not on Y. Because we clearly stated that X is conditionally independent of the variable Y. X is free from the existence effect of Y. Okay. So there is relation between this definition and our use of conditional independence in the definition of the naive-Bayes classifier. Did you understand? In naive-Bayes classifier, we use posterior probability of H given the training examples. Means hypothesis to become true, to be more probable, it depends on the training examples that is provided. If you provide good set of training examples which is unbiased, then you can easily prove that this hypothesis will be true. This hypothesis is more probable. The probability of that hypothesis increases in accordance with the set of training examples provided. That is why you write it as probability of H given D. Here we are writing it as probability of X given Z by eliminating the conditionally independent variable Y. Okay, so you are able to find some relationship between naive-Bayes classifier and Bayesian belief network. It will be more clear for you as you go further. Now the naive-Bayes classifier assumes that the instance A1 is conditionally independent of the instance attribute A2 given the target value V. Now let us make it more simple and represent it with respect to Bayes theorem, naive Bayes classifier, and slowly come back to Bayesian belief networks. Let us start from the more understood topic, that is naive Bayes classifier, and slowly arrive at Bayesian belief networks. Okay, lot of research is going on current days in Bayesian belief networks and its application in various domains. Okay, so if you read blogs on that, you will understand how exactly the current research status is. Okay, now let us see. The naive Bayes classifier assumes that the instance attribute A1, say sky, is conditionally independent of the instance attribute A2, say humidity, given the target value, playing tennis on that particular day, if it is say S. Now, this allows the naive Bayes classifier to calculate probability of A1, A2 given V. Understand this carefully. Probability of A1, A2 given V. In the equation, how do you calculate that value, probability of that value, whether it is yes or no for that particular instance? How do you calculate? By maximizing, you know this formula. In the last class, we have derived this. Probability of that value existing separately, probability of that outcome variable, label, probability of the target label existing separately, irrespective of any attributes, multiplied by product of probabilities of each of the attribute given the target label. That will give you the probability of yes and probability of no when you are predicting whether tennis can be played on a particular day given the weather conditions. Right? What is that? You're maximizing the probability of the target label separately multiplied by the product of each attribute existence given the target label as yes or given the target label as no. Okay, this is what we have derived in order to calculate the probability of yes and probability of no. Now, this can be represented according to this first point. What we have considered, attribute A1 is conditionally independent of attribute A2 given the target value. So, what is the probability of A1, A2 given the target label B? It is nothing but the probability of A1 given A2. What is the dependence between both the attributes first? The probability of, what is the independence between the attributes first? Okay, so probability of A1 conditionally independent of A2 given V. Okay, this can be written like this. Probability of A1, A2 given V. How do you write it? Probability of A1 which is conditionally independent of A2 given the target label V multiplied by probability of A2 given V. Right? Now this can be further simplified as, because A1 is conditionally independent of A2, you can eliminate it according to conditional independence formula. So how do you write it as? Probability of A1 given V. This term is eliminated. So probability of A1 given V multiplied by probability of A2 given V. So now can you see how it is simplified? Probability of A1, A2 given V is written simply as probability of A1 given V multiplied by probability of A2 given V. This is according to our naive Bayes classifier. Probability of two attributes occurring given the training example can be calculated as probability of A1 given the target label and probability of A2 given the target label. It is product rule, you remember, right? probability of A and B occurring together is probability of B given A multiplied by probability of A. Okay, so whenever you want to find out the probability of occurrence of two events together, it is the product of first event occurring and the second event occurring. Given those two values are conditionally independent. Remember, A1 and A2, if you're taking two attributes, if you want to find out the probability of them occurring together, given the condition they are conditionally independent, they doesn't have any relationship between each other, then you can calculate the probability of both of them occurring together as product of each of them occurring separately. Probability of A1 multiplied by probability of A2. But here we have a conditional probability given V. That is why we have attached given V here. Did you understand this? Very simple, right? You have just reduced the representation to a more simpler form. Now, how Bayesian belief networks are represented. Why do you call them as belief network? Because if two variables X are, say if X is determining Y or Y is dependent on X, means the probability of Y is dependent on the probability of X. Probability of you coming into this world increased because of your parents already existing in this world, right? Means the belief of the parent existing, the probability of the parent existing will determine the probability of the child existing. Means it is providing some belief, it is providing some confidence by asserting dependence between the variables. Dependence, I'm talking about dependence, not independence. By assuming there is dependence between some variables. That is why that belief, that support is provided by the network. That is why we call them as Bayesian belief network. Okay, now see in this case, in this diagram, you can see that storm determines lightning and lightning determines thunder, right? Or we can read it as thunder is dependent on lightning and lightning is determined by storm or dependent on storm. Okay, now if we take campfire, campfire is conditionally dependent on its predecessors. What are the predecessors? Storm and Bastur group. They conditionally determine this campfire, or campfire is dependent on its predecessors, Storm and Bastur group. Got it? Now we can also say that campfire is conditionally independent of lightning and thunder. Can you tell me why? Because lightning doesn't have any relationship with campfire in this diagram, and even thunder has no relationship with campfire in this diagram. Did you observe that? So we can say that campfire is independent of its non-predecessors. These are not predecessors. Storm and Bastur group are predecessors of campfire. Lightning and thunder are not predecessors. Predecessors means you, your predecessors to you. You are successors to your parents, like that. Okay. So lightning and thunder are non-precedents of campfire. That is why campfire is independent of lightning and thunder. Campfire is determined conditionally campfire is conditionally dependent on storm and Bastur group because they are its predecessors. They are its parents. Okay, Storm and Bastur group are its parents in the particular network. That is why campfire is conditionally dependent on storm and bus tour group. Did you notice now in this diagram? All the nodes indicate the variables and all the arcs, these are called as nodes. These are variables. And all the arcs, the edges between the nodes, they are called as dependencies. Relationship between the nodes. Got it, students? Did you understand this network now? Now, did you notice one thing here? Some variables are dependent on each other and some variables are not dependent on each other. Now, lightning and campfire are not at all dependent on each other. Thunder and forest are not dependent on each other, right? But storm and campfire are dependent. Bus tour group and campfire are dependent. So what did we understand? Partial assumption of conditional independence is still in picture. In Bayes classifier, you have the concept of complete conditional independence. But in Bayesian belief networks, you have partial conditional independence. Some subset of attributes are conditionally independent. Some subset of attributes are conditionally dependent. Okay, so that this makes a task easier. If there are some variables that can't be measurable, you can still derive those variables from linear combination of other variables by forming an equation of other variables. Got it? So a Bayesian belief network represents the joint probability distribution for a set of variables. About this table, I'll explain you later. Okay, you understood how a Bayesian belief network is represented. It can represent conditional dependencies and independencies between the attributes. Now the Bayesian network in the figure represents the joint probability distribution over the Boolean variables. Why we are calling Boolean variables is storm, it is existing, yes or no. Lightning, did it occur, yes or no. Thunder, did it occur, 0 or 1, like that. You have only two possible values allowed in this particular example. That is why you're calling them as Boolean variables. Now the Bayesian network in the figure represents the joint probability distribution over the Boolean variables storm as a node, lightning as a node, thunder, forest fire, campfire, and bus tour group. All these are the nodes. And the connections between them explains the dependency between the nodes. Now, a Bayesian network represents the joint probability distribution by specifying a set of conditional independence assumptions represented by a directed acyclic graph. Acyclic graph means, say you don't have connection back to the predecessor. Say you have a node like this, you are having a successor node like this. Now you don't have another connection back. There is no cycle in the connections. Then we call it as directed acyclic graph. If there is no such node that forms a cycle, you call it as directed acyclic graph. Okay. Now a Bayesian network represents the joint probability distribution by specifying a set of conditional independence assumptions. Yes, conditional independence assumptions are specified in the network, right? Here in this case, campfire is conditionally independent of lightning. Campfire is conditionally independent of thunder. Got it? So it mentions conditional independence assumptions together with sets of local conditional probabilities. You have some conditional probabilities mentioned locally. Let us see how they're mentioned in the table. I'll explain you. Now each variable in the joint space is represented by a node in the Bayesian network. Yes, we know that. Now for each variable, two types of information are specified. What are those information specified in the Bayesian belief network? First, the network arcs, the edges between the nodes, the connections between the nodes, the arrows between the nodes. They represent the assertion that the variable is conditionally independent of its non-descendants. As I said, non-descendants means thunder, lightning. These are non-descendants for campfire. Okay, or not predecessors for campfire. So they are conditionally independent. That is how you need to understand. In the network, given its immediate predecessors in the network. I'll go back once again. Now, campfire, listen carefully, campfire is conditionally independent of lightning and thunder given storm and bus tour group. I'm repeating, campfire is conditionally independent of lightning and thunder given storm and bus tour group. I can say like this, because lightning and thunder are not predecessors of campfire, but storm and bus tour group determine campfire, has some effect on setting up a campfire. That is why when I say probability of campfire is conditionally independent of lightning given storm, I can eliminate lightning and I can simply write probability of campfire given storm. That is your conditional independence definition in the Bayesian belief network. First slide, what I have shown you. Okay, go back after the class if you have a doubt. Now, what is the second information this Bayesian belief network provides? Second, a conditional probability table is given. We haven't talked about that still, right? That conditional probability we haven't spoken it. I'll explain you what it is. Second, a conditional probability table is given for each variable. Each variable, they'll provide the conditional probability table, describing the probability distribution for that variable given the values of its immediate predecessors. If the values of its predecessors are given, then what is its probability distribution? That is also given. That is actually given in the table. I'll show you. The joint probability for any desired assignments of values y1, y2 and so on up to yn to the tuple of network variables y1, just assign a angle bracket here so that you can represent it as a tuple. To the tuple of network variables y1, y2 and so on up to yn can be computed by the formula. How do you compute that? Probability of all these variable values occurring is equal to product of probability of each of those values given its parent's probability, given its parent's value. Right? Means probability of occurrence of thunder will enhance or reduce, will increase or reduce the probability of occurrence of, sorry, I have told you the other way. Probability of occurrence of lightning will increase or reduce the probability of occurrence of thunder. Right? So lightning is the parent of thunder. Can we say that? Means probability of thunder can be calculated given probability of lightning. That is parent of yi. Yi is thunder here. Parent of yi is lightning. Okay. So probability of y1, y2 and so on up to yn, the desired assignment of values, that probability can be obtained as product of, do not get confused with sigma. We are talking about the product rule only. Okay, because we are working with conditionally dependent independent variables. When we talk about conditionally independent variables, you have to talk about product rule. So pi, you are using the product of I equal to 1 to n. It is nothing but the probability of each of those variable values given its parents' values, given its parent variable values. Means probability of a thunder equal to 1 given parent lightning equal to 1 or lightning equal to 0. If lightning equal to 1, probability of thunder increases. If lightning equal to 0, probability of thunder reduces. That is how you calculate the probability of each of the variables by considering its parent's probability. That is why you have written this generalization of the concept. in mathematical terms. Okay, here parents of yi denotes the set of immediate predecessors of yi. So thunder's immediate predecessor here, thunder's immediate predecessor is lightning. Campfire's immediate predecessor is storm or Bastur group. Forest fire's predecessors are lightning, storm and campfire. Like that you have to understand. Now, when you are calculating forest fire's probability, you have to calculate the probability of lightning, storm as well as campfire, because these three are its immediate predecessors, parents. Okay, now note the values of probability of yi given parent of yi are precisely the values stored in the conditional probability table associated with the node yi. So whenever you are asked to calculate the probability of the child, you will be given the probability of parents occurring with the child and combination of parents occurring, not occurring with the child. I'll show you how. Now see in this table, the table is visible clearly for you. The Bayesian network in this figure represents the joint probability distribution over the Boolean variables storm, lightning, thunder, forest fire, campfire and the Bastur group. Yes, we know that. Now consider the node campfire. Let us focus only on this node campfire. Now the network nodes and arcs represent the assertion that campfire is conditionally independent of its non-descendants. These are not its descendants, right? Neither are its predecessors. So it is conditionally independent of lightning and thunder. Non-descendants lightning and thunder. Given its immediate parents, storm is parent of campfire and Bastur group is parent of campfire. Means occurrence of storm, probability of occurrence of storm and probability of occurrence of Bastur group will increase the probability of occurrence of campfire or reduce the probability of occurrence of campfire. In general sense, we know that when storm occurs when Bastur group comes for a trip, then campfire will be established. That is common sense, but probabilistic approach support. That is why I'm saying may increase campfire, setting up the campfire may increase or reduce because you think I don't have common sense. So in that case, campfire, I can't say that occurrence of storm and Bastur, both of them coming together will increase the probability of campfire or reduce, but it is dependent. I can say that because storm and Bastur group are parents of campfire. But when you calculate the probabilities, you will come to know whether it is increasing the probability or reducing the probability. Okay, but there is a relationship, that much we can say from the network. Got it? Now this means that once we know the value of the variables storm and Bastur group, the variables lightning and thunder provides no additional information about the campfire. Beautiful line. This means that once we know the value of the storm, you know the value of storm, you know the value of Bastur group, then you can assess their impact on campfire, but lightning and thunder doesn't give any additional information about the campfire. That is why we say that campfire is conditionally independent of lightning and thunder. Now the right side of the figure shows the conditional probability table associated with the variable campfire. Now listen how to understand this table. Now setting up a campfire, if it is yes, how it can be calculated? It is dependent on storm and the Bastur group occurring together. Now I'll read it the other way. The probability of setting up a campfire given storm occurred and the Bastur group, its probability is 0.4. Now, the probability of setting up a campfire when storm occurred but Bastur group didn't arrive. So the probability of setting up a campfire is 0.1. Did you notice here the probability has reduced? Why? Because Bastur group haven't arrived. So there is no necessity maybe in setting up the campfire. That is why probably its probability reduced. Now, the probability of setting up a campfire when the storm didn't occur, but the bus tour group arrived, it is 0.8. Because normally the tour groups, they tend to set up campfires irrespective of whether a storm has occurred or not. So it is 0.8. Now, probability of setting up a campfire when storm didn't occur and bus tour group didn't arrive, probability is again low, 0.2. Now come to the next line. Probability of not setting up a campfire. Did you see the negation symbol here? Negation of C. That indicates not setting up a campfire. Now, probability of not setting up a campfire, when storm happened and bus tour group arrived, it is 0.6. And probability of not setting up a campfire, when the storm occurred and bus tour group didn't arrive, it is 0.9. Yes. That is obvious, right? And probability of not setting up a campfire when storm didn't occur, but the bus tour group arrived. It is 0.2. Now, probability of not setting up a campfire when storm didn't happen and bus tour group also didn't arrive. It is high, 0.8. Now, once again, did you notice this sum of probabilities is 1? This sum of probabilities is 1. This sum of probabilities 0.8 plus 0.2, 1. Here the sum of probabilities 0.2, 0.8 is 1. Okay, so the probability is distributed across the occurrences of campfire, if it is yes or no, based on its parents' probabilities, whether they have occurred or not. Generally, they'll give you this kind of conditional probability table and they'll ask you to calculate the probability of setting up a campfire or calculate the probability of generation of a forest fire, like that. Okay, so did you understand now? Because of the dependencies between the attributes in the Bayesian belief network, you will be able to calculate in a more better way the values of nodes which are actually not measurable. Okay. So the top left entry in this table, for example, expresses the assertion that, what is the assertion? Probability of campfire becoming true, setting up a campfire, given storm true and bus tour group true. What is the probability? 0.4. That is how you can write. It is more clear for you. Note this table provides only the conditional probabilities of campfire given its parent variable storm and bus tour group. Now, if at all you are asked to calculate the probability of thunder, then you might have given the probability of lightning. And if you are able to calculate the, if you are asked to calculate the probability of forest fire, you will be asked to, you will be provided with the probability of lightning, probability of storm, probability of campfire, because these three are parents of forest fire. In that case, how many combinations you get? For these two variables, you get 4 combinations, right? Now, when you have 3 parents, you will get accordingly extra combinations. Lightning occurring, storm and campfire not occurring. Storm occurring, lightning and campfire not occurring. Campfire occurring, lightning and storm not occurring. That event not occurring. Like that, you will get various combinations and all those probabilities will be given, which will help you to calculate the probability of a forest fire being generated or a forest fire not being generated. Okay. So the set of local conditional probability tables for all the variables together with the set of conditional independence assumptions described by the network. From the network, we can know what are the conditional independence assumptions. From the table, we can know the set of local conditional probabilities. Okay. Now it describes the full, from this we can calculate the full joint probability distribution for the network. It is easy to calculate the full joint probability distribution for the entire network. Now online you have lots of examples to understand this Bayesian belief networks in more depth. Okay, so if you are further interested, you can refer to those examples of Bayesian belief networks. Okay, this example is sufficient for you to understand the basic concept. But if you are interested to know further, then you can refer online resources. Now, what are the inferences we have made? We might wish to use a Bayesian network to infer the value of some target variable, say forest fire in this case, given the observed variables of the other variables. Now, you can't measure a forest fire until it has occurred, but nobody wants that forest fire to happen at all. In that case, what is the probability of a forest fire being generated? You can calculate it from the probability of other known parents of forest fire. That makes your work easier. Okay. Now, given that we are dealing with random variables, it will not generally be correct to assign the target variable a single determined value. Okay. Now, what we really wish to infer is the probability distribution for the target variable, which specifies the probability that will take on each of its possible values given the observed values of the other variables. Now, other variables' observed values are given. You can easily calculate the probability distribution of the child value when the local probability distributions are available to you as a table. Okay. Now, this inference step can be straightforward if values for all the other variables in the network are known exactly. Other variable values should be known exactly. Only then you can infer the value of, say, forest fire, the child node, from the parent nodes. Now, in the more general case, we may wish to infer the probability distribution for some variable, forest fire, example is being given. Given observed values for only a subset of the variables, thunder and bus tour group may be the only observed values available. Now, in this case, we can infer the value of forest fire from the known variables. Say other variable values are given, thunder and bus tour group, like that. Now, in general, a Bayesian network can be used to compute the probability distribution of any subset of network variables. So sometimes you may also have subset of network variables which are determining its child variables. Take those probabilities and you can see its effect on occurrence of its child variables, probability of its child variables, given the values or distributions for any subset of remaining variables or child variables. Okay. Now, in the next class, the last concept of this module, the expectation maximization algorithm, we are going to cover. Any doubts in this, students? We are late by 4 minutes, sir. Shivkumar sir, I'll end the class. Okay, we'll meet in the next class.